Welcome back. So in this video, we're going to utilize this formula and create a confidence interval and see an example. I've got one loaded up down here. This is about abalone. And I'm not sure if you're familiar with abalone, but they are a really cool mollusk. And I'm going to show you a couple pictures here from the good old Google. This is the species red abalone, and they've got this really brilliant red shell. A lot of people cherish them because of the inner side, the inside, which has the mother of pearl inlay. It's quite nice. So they live on the ocean floor, and I was a part of a team that went out and measured hundreds and hundreds of abalone. In this data set, I've only got 116 that we're working with, and the length was measured. So over here, we've got the sample mean length in centimeters, so about 17 or so centimeters, and the sample standard deviation, 3.3 centimeters or so. So we've got a lot of the info that we need here to create a confidence interval. Now this is sample data, right? So we've got N over there. This is Y bar. This is labeled as S already. Right? We know about this sample. What this confidence interval is doing, I'm going to scroll up here. This is a confidence interval for the population mean. It's a way to estimate the population mean, because we know that the sample mean is not going to equal the population mean. But once we create this interval with this margin of error, we are hoping to capture the population mean in that interval. And so that's what we're going to do here, is create this interval. Back up to the formula. We have the sample mean, the point estimate. We were given the standard deviation of the sample and the sample size. But what we don't have immediately accessible is this t critical value. That t value over here in this pink tick mark that defines this region. So we need to go figure that out. We're going to need our t-table, and we're going to need to think about what is the degrees of freedom and what is alpha. Okay, so let's consider what the degrees of freedom is here. Degrees of freedom is just n minus 1. Since our sample size is 116, our degrees of freedom is 115. Sweet. Well, now what is alpha? Well, we were told that we have 95% confidence, or that was what was instructed of us. So since we have 95% confidence, that the complement is alpha, 0.05. But we need to split that in half for the two tails, 0.025. With this information, we can now find our t critical value, because now we know to go to the t-table with 115 degrees of freedom and 0.025 as the upper tail area. So I'm going to display the t-table here, and we know where to go. Okay, so I'm going to scroll down. I see the column that says 0.025, and I want to go to the degrees of freedom. Hopefully that says 116. Now, we don't have 116 on this t-table, but we had mentioned in the previous video, we can just use the closest degrees of freedom. So I'm going to use 100, because that's the closest to 115 here. And the column that corresponds to 95% confidence. And there is sort of a nice little tool right here where it says 95% confidence. So you can use that tool in the very bottom of the table to help you find which column you need to go to. But remember, the way that this table is, or the way that the notation is developed, it refers to the area in the upper right tail. But you can use both of those to your advantage. So I've got the T critical value of 1.984. So I'll make a note here that we used the closest degrees of freedom, which was 100. We could also use R to determine the T critical value. I've got our essential info up here for this problem, and the function that we would want to use is QT, because PT finds probability. We already know the probability in the upper right tail. So QT is going to get us the T value that corresponds to a particular probability. So I'm going to input into the QT function not 0.025, because that's the area in the right tail. I need to actually do 1 minus 0.025, comma, the degrees of freedom here. We'll go ahead and use 115. We're not limited to the table here, so we'll type it in as it is. So our T critical value will be 1.9808. Now that's pretty dang close to what the T-table provided us. It's off because the T-table we had to use 100 degrees of freedom due to its limitations. So pretty dang close though. If we had typed in only 0.025, we would get the negative of the desired value. And that is because of symmetry with normal distributions. For the rest of this problem, however, we'll go ahead and continue with the value from the T-table. Now that we have all of the components that we need to create this confidence interval, we are now going to plug them all into the formula. So it starts with the sample mean, 17.368. Add, subtract the margin of error, which is composed of the T critical we just found, multiplied by S over square root of n. So I'm going to take it nice and slow here and compute first the standard error estimate. So let's use our calculator to find this S over square root of n. 3.358 times, divided by actually, the square root of 116. So that is our standard error for the mean. And while I'm here, I may as well take that quantity and then multiply it by the T critical value that we had, which was 1.984. So this is now the margin of error. Okay, I will transcribe that. Now that we have the point estimate, the sample mean, plus or minus the margin of error, we are ready to perform the last step of our calculation. This is going to get us the interval. This is actually more like 2 steps here, because we need to take the mean plus and minus this margin of error. And since I've got r here, I'm going to give this a name, margin of error. And I already know the mean was 17.368. And we do minus the margin of error, and then the mean plus the margin of error. And these are going to be the lower bound and upper bound of the confidence interval. And let's watch it whip. So I need to make sure MOE is defined, and now I can compute the lower and upper bound. I realize I've misspelled upper.
That is 16.749 up to 17.987. Because this was measured in centimeters, we should include that for completeness.
And this is our answer. So I'm going to put it in a box, and that feels great. This is our 95% confidence interval for mu. The particular way that this is written, this is called interval notation. We have the lower bound on the left and the upper bound on the right. So that is how we utilize this formula to create a confidence interval. Well, that's great. That was an example of using data to construct a confidence interval. Now this was a 95% confidence interval. I'm going to write that here, 95% CI for mu. Remember, we don't know mu. We don't know the population mean. So let's discuss how to interpret these values. Interpretation. Again, we don't know the population mean mu. And so we also don't know if the population mean is contained within our confidence interval that we created in the box above. But what we say is that we are 95% confident that our confidence interval contains mu. The way that this interval was constructed, the basis of this formula is such that a large percentage of random samples will form confidence intervals that contain the population mean. Because this was a 95% confidence interval, we are thus 95% confident that mu is in there. This requires remembering the sampling distribution perspective of all of those theoretical samples that exist. We don't go and collect an infinite number of samples, but they do exist. And if we collected all of those samples and computed the sample mean for each along with its confidence interval, then 95% of those random samples will contain mu. But a small percentage, hey, check that out, isn't that alpha? Will not contain mu. This sample data came from just one of those many samples that exist. We do not know if this particular sample is one of those winning confidence intervals, one of those winning 95% of confidence intervals. And that is a part of why we say that word confidence. We are 95% confident that mu is contained within those bounds that we calculated.